the plane when it is just crossing the the Bay of Bay of Thailand and swimming back to the shore. What I need displacement, right? I have strain diagram given over there already. So how do you come up with displacement?
Yeah.
You just need to integrate, right? So displacement, strain at a point, okay? If you consider one point, you have strain value multiplied by dx. It is an infinitesimal displacement that is caused by this strain at point x, okay? So you need to integrate this up, all right? So delta is basically equals to the integration from 0 to L of this strain, okay? Function of strain multiplied by dx. So f L minus x over EA dx. I think you should understand the meaning every time I perform any integration or when I do all mathematics over here on the board. Okay? I'm not just doing integration because the formula say integrations. I'm doing integrations now because I can come up with little displacement. So this little displacement will be what? The d delta, okay? Little displacement that is caused over one point is the strain multiplied by dx, okay? This is the original equation. So when you want the total delta that is occur over x equals to 0 to x equals to L, you need to sum this up, okay? But this summing up, okay, is conducted in the form of integration. Okay, so you have strain over here, strain times dx, and then you integrate it up, you get delta. Okay, integrate this one. Life is very easy, right? Because you can pull out FL over EA outside, okay? Like this, 0 to L. So you have L minus x dx turns out to be FL over EA, okay? Lx minus x squared over 2. You evaluate when x equals to 0 to x equals to L. When x is equals to 0 or 0, x equals to L, you get L squared minus L squared over 2. You end up with L squared over 2. So the delta is equals to FL cubed over EA. Let me check. I get I pull out the L, okay. So FL squared, alright, over EA, divide by 2. Okay. So what is the condition that we need to satisfy? We have to make sure that delta F adds up with delta P turns out to be 0. Okay? So delta F, which is FL squared over 2EA, adds up with delta P. Your delta P is going backward to the left hand side. So the sign of the delta P has to show up as the negative sign PL over EA. And this relationship must hold, okay, in order to calculate the effects of the equivalent nodal point reactions. Cancel out, cancel out, cancel out, cancel out. Find that we have the P equals to FL over 2. Okay, just easy. Actually, it's just distributed half to one node and another half to another node. Alright? Then, if you have P equals to FL over 2, so here's the thing. Over here you have backward equals to FL. Alright? Okay, you are going backward equals to FL. For this one, your P forward equals to FL over 2. So if I point the direction like this, okay, then this will be minus FL over 2. Right? How about this point here? This point here, for this primary system, you don't have anything acting at this node, but you have the P acting on the right node. So you end up with the P, which is FL over 2 acting over here. So finally, you end up with this one, FL over 2 and FL over 2 acting on these two nodes. Okay. And then if you want to put it into the vector form like that, well, you will need to put the sign, okay, in the way that is consistent with the x that you use in the derivation of the stiffness matrix and etc. So your FL over 2 will be minus FL over 2 and minus FL over 2. Just like that. And then I can play a lot with this one because I can just change the cross section. Okay, I could put variation in the geometry. Okay, and then okay, force vector will be different. But okay, for the standard truss element, generally you will find that okay, standard one that is available in the software, commercial software, you have just a constant cross section truss. But okay, if I want to test you, like if I want to know if you understand things well, I can just put you in the different situations, just a little bit different from this one, and then ask you, okay, what might be the force on them. I may just put one system, okay, not too big, but if you do the direct stiffness without any help from this stuff, okay, your system will be like 12 degrees of freedom. But if you don't do it that way and then you simplify your life by the knowledge a little bit, then you end up with much less degree of freedom. Then that could be the case. Alright, this is a bi element. So what if I change something like can I clean it? You're done, right? Okay. So I'm gonna load you all on the plane again and then see if I throw you in the Pacific Ocean right now, then will you swim back? Okay, so let's make it Fx over L. Like this, okay? Could it be homework assignment? And then you will find it out. I just add something there. You used to have just uniform distribution. You just make it linear distribution of the force intensity. So how does the force intensity looks like? How does it look like? Yes, it looks like that. So this is intensity of force. So you have force equals to F unit force per unit length over there at the end. At x equals to 0, your force intensity is equal to 0. Okay, just understand that. Okay, it is the magnitude of force. So you have a small magnitude over here, and then gradually increase linearly with the x. Okay, all right. Now you get the force intensity like so. What to do next? Well, still, you do it the same way. You have two unknowns, so you cannot do it in one shot. You need to break this system into two. One primary structure, which is subjected to this thing here, this force distribution. Another one Okay, is this system. This system is easy, okay, because you will end up with the PL or EA all the time. You will not get anything different from this one here. But how about this one? This one right now, things change, right? So you need to compute to produce the what? Internal force diagram, okay, from this new one. Okay, so here you have the F x over